All right, for our next section of this chapter, we need to discuss the uses of these correlation coefficients. So we've talked about what we do with them, how we get them, how we calculate them and make our decisions. For every other hypothesis test this semester, we've known what the use was. The use was to determine if a treatment was effective in changing a dependent variable or not. That's kind of what they all had the same use, evaluating the efficacy of a treatment. Well, these aren't about treatment, so there's other things we use them for. So there's four pretty common ways we use correlation coefficients. One of them is to make predictions. If I've established that there is a relationship between two variables, means I've done the math and I've rejected the null hypothesis and said, yes, there really is a pattern here. Again, think of the classic example, height and shoe size. Or we could go with something a little less obvious, education and income. We know there's a pattern there, that the higher the level of educational attainment a person has, in general, the higher level of income that person earns. Another positive correlation coefficient. One value goes up, the other goes up with it. Well, what that means is if we've established that there is a pattern, then if I know the value of one of the variables, I can predict the other variable with a known degree of accuracy. So this is common if we think about why do universities, not CSN so much, but why do universities make you take SATs and ACTs and GREs and MATs and LSATs and MCATs, all these entrance exams to get into their programs? It's for the purpose of prediction. In general, the higher you score on those tests, the better you're going to do in school. How do we measure that? GPA. So the higher your test scores are, in general, the higher your GPA will probably be, right? No relationships are really perfect in that regard, but that's what they're using them for. They're saying, oh, if you bomb this test, you're probably going to get a bad GPA and you're going to make our school look bad by flunking out or not graduating. So we want people that are going to do well. And how do we predict that with these tests? So I could predict your, if I knew your education, I could predict your income level. If I knew your ACT scores, I could predict your GPA. Now, how well am I able to make that prediction? So most of the semester we've other than conceptually talking about, we've not really gotten into these issues of effect size and those sorts of issues. This is the first time we're going to look at that because it's a very, very useful thing in this chapter in particular. It's called the coefficient of determination. What the coefficient of determination tells me is how much of this relationship is free of error. In other words, how much of it is rock solid and how much of it seems to be kind of random chance. It's a very, very simple calculation. Simply take your R value and square it. So let's look at a couple simple examples here. Let's pretend for a moment that our correlation coefficient, our R value, we happen to get a perfect score. Our R is 1, right? We know that represents perfection. Well, our coefficient of determination would also equal 1. Now, what we're going to do is basically just sort of drop the decimal, multiply it by 100, if you will. What that would tell us is with a Pearson R value of positive 1.00, 100% of that pattern is free of error. Means there are never, ever any exceptions to the pattern, not even a whisper of deviating from that pattern. So what this says is the coefficient of determination is 1.00. But what that means is if I knew the value for variable x for you, I could predict the value of variable y with 100% accuracy. If this was height and shoe size, which it wouldn't be, but if we got this value for height and shoe size, if you told me how tall you are, I could predict your shoe size 100% accurately every time. Why? Because there are no exceptions. We would find the same thing if we went to the opposite extreme and said our R value was a -1. That's also perfect. It just means that they move perfectly opposite to each other. So our coefficient of determination would still be a 1.00, but turning that into a percentage, I would still be able to, if I knew one, predict the other with perfect accuracy, 100% accuracy, no error. Let's look at a completely different sort of example. Let's say we had an R value that's also kind of a perfect score of 0. Let's say we landed exactly in the middle. With our book problem, we almost did, right? 0.06, but let's pretend we got a 0. 0 is perfect independence. There's not even a random coincidence of a shadow of a pattern here. Well, our coefficient of determination, 0 squared is 0. That's the 0% accuracy. That says that there is nothing solid about this pattern. It's 100% random. And so if you knew the value of one predicting the other, if you got it right, it was a lucky guess because the data didn't help you. But now let's go with a couple more less extreme examples just to see. Let's say we had a correlation coefficient of 0.25. So it's fairly small, fairly modest. Well, all we've got to do is square it. So get your calculator. 0.25 squared is 0.0625. So again, we're going to round. 0.06 is what that rounds to. So what does that tell us? That this pattern is 6% reliable. That if I knew the value of your score for X, I'd have a 6% chance of knowing the value for Y. It means there's 94% error, right? So that's telling us that's a really weak pattern. Let's look at something more like a 0.75, much stronger thing. Well, again, take our calculators, 0.75, square it, and we see 20.25. So again, we're going to round that as 0.20. Even with a value as high as 0.75, I know that it's 20% real, that pattern, 80% error. I could predict one pattern or one variable from the other correctly 20% of the time. That's our coefficient of determination. This helps. We'll talk about this in a different way on a different board down the road today. But this helps us to take these numbers and put them in terms that are easy for us to understand. When you're looking at published research that uses correlation coefficients, there's often dozens and dozens of them. They put it in a big table, a big matrix table. It's just all these numbers everywhere. And you can kind of get number blind with it because the numbers aren't easy to relate to. They're not something that is intuitive. But simply by squaring it, you take it from an unrelatable number and you put it in terms that are very relatable in everyday terms. So it's a very powerful and very useful thing to do. So we've only got one item done on this list, but we spent some time on it. So I'm going to stop the video and pick it up with number 2 on this list.